My name is Phil Lyons. I'm the Technical and Commercial Director for Advanced Plastics. Advanced Plastics established 30 years ago now. We're now approaching £30 million turnover with in excess of 200 people here on site. One of the ways the business has developed over the years is we've really focused on providing good quality support for our customers in the area of DFM, which is design for manufacture. We take their ideas and make them manufacturable. That's really the area we focus on. And it was really in the last 2 years what we thought would give us a significant advantage if we could physically produce one of our customers' components in its concept stage, so we can assess it physically, tangibly, so we could touch it, see it, we could check it in various different ways. 3D printing has given us the opportunity to just enhance and deepen and be more effective in our design for manufacturing process.
Hi, my name is Thomas Lyon. I'm a graduate project engineer here at Advanced Plastics. So when I joined Advanced Plastics, there was much talk about 3D printing. We already had some components which we were using in our company which were 3D printing, but before this all of these parts had been produced through external suppliers. And there was much speculation into getting a 3D printer. The word had been thrown around throughout the team, but really when I came in I saw the opportunity that we could use this 3D printer to produce not only the parts that were already having 3D printed, but I also saw some other applications we could definitely use the 3D printer for. For example, we've got these components here, which are part of a cell. Is an automated process for assembling two components. So this is our mixer cell, so the parts which we've shown which are 3D printed are on the assembly jig in the back. This cell has two injection moulding machines. One's producing a black mixer, the other one a clear nozzle. The assembly station there takes the black mixers, drops them through a chute, which is 3D printed, which is then dropped into the nozzle below. That is then taken to a further assembly jig which creates a press fit, and that's your finished component. This was our first application. This is actually what we worked with the supplier of the printer to basically see where the quality stood against our components, current components, and the components we could get produced off an S5. And then from that point, having our own printer I saw as an advantage because we could print these components a lot cheaper than we could get them outsourced, and also allowed us for a quicker lead time and to manage design revisions a lot quicker because the lead time will be shortened. So this is our thread ring cell. We run multiple variants of this part, and this is where we're currently trialling some of our 3D printed parts. These are the thread ring grippers, which are made from nylon, and we're currently trialling these against the original aluminium ones to see how they perform and hold up against the 24/7 abuse and use that it gets out of this machine. So originally the grippers on this thread ring cell were made from aluminium, and they were very expensive to produce. We basically didn't obtain the right to the CAD file, so we had to go through a certain supplier, which cost us a lot of money. One of the options we had with the 3D printer was that we could reverse engineer the part and then 3D print them ourselves. What we can see here is just a batch print of these grippers. Wasn't a clean-cut process. Initially we started with a PLA plastic, but as these are injection molded parts, they come off the press at around 180 degrees. So we found that with the PLA printed parts, it was slightly deforming the PLA grippers. And we then looked out for further advice and actually chose to move to a nylon brand of filament and reprinted the parts at a higher infill density and wall thickness. And since that point, there's been no downtime reported from these parts, and the damage on them has been recorded as minimal, considering these parts run 24/7. One thing the 3D printers allowed us to do is produce prototype parts. So part of our automated engineers' tasks are projects and basically continuous improvement projects, and one such one required a prototype robot head to be made for use of picking up the parts and basically proving a concept. So the robot head I've got in front of me here was printed from PLA, and it's quite complex, and basically our alternative to 3D printing this would have been machining this, and since it's quite complex, could have set us back a lot of money. And sometimes when something hasn't been proven from a concept stage, it can be quite hard to get the backing to basically fund this project without proving it's going to work. So the 3D printing here has allowed us to 3D print a robot head to basically prove a concept, which it did flawlessly, and from this was able to build his case study for obtaining the funding and the support to go ahead with the full-fledged project. So one of our recent case studies that's come from our place, actually from one of our automation engineers, was he recognised a process on the shop floor that was occasionally failing due to misplaced inserts on a tool, basically due to the robot head design, which was picking up the inserts, was occasionally missing them, which would cause the tool to go down and obviously reduce our OEE, so our overall equipment efficiency. So he took it upon himself to improve this process, and he first analysed the situation and looked at it, designed a more conformal set of grippers which could pick up the inserts and place them onto a jig, which would then place them into the tool to be overmoulded around. This solution he was able to firstly prototype using PLA. The print lead time was around a couple hours. He would then test that revision and make his modifications, generate a second revision, which then was put onto the machine initially for a trial and testing. And we was first anticipating that because they were PLA, they might wear out quite quickly. So we created a full separate set out of nylon. However, those grippers have been on the machine since that trialling phase, and have apparently overall increased the equipment efficiency by 20%, which is massive because the part is quite a big runner. So over the time that machine runs, it's quite a significant improvement. And like I say, with the 3D printer, these parts we've been able to create spares, and so now a full set of spares available if there was any accident or unfortunate event which meant we'd have to replace them, and there would be no downtime. This is our rocker cover assembly jig. This here is something we've 3D printed in-house, and it's a holding jig for the rocker cover. So the machine picks the inserts off this part here, places them into the tool. We then get a part which comes to us on this jig. So the part is placed there by the robot, which then holds it in place. The operator then uses the assembly station to apply these inserts. And once these fixes are put on there, we then place it back into there, close it up. The robot then picks the rocker cover back up and checks that all of those inserts have been put in place.
We've been able to be much more innovative in the designs of our robot heads, in our automation cells, and really fine-tune things and try things out in a much more controlled and effective manner, and much more dynamically through having the facility 3D printed, because we can take an idea and try it within 24 hours. So yeah, we're still in its infancy, but you know, we're very confident it's strengthened what we do, and we'll continue to improve with it.